be appreciated yesterday.
I feel like I'm just trying to sell the subject. You guys are buying it. All right, so trig 2. We're going to start off talking about inverse trig functions. So we did a little inverse trig functions yesterday with finding the angle whose tangent or sine or whatever is some value. We'll do this in depth. We will do some applications of the fundamental trig identities that we saw yesterday. And then we'll talk about sum and difference formulas for an angle. So if you take the sum of two angles, the trig function of the sum of the angles is related to the trig functions of the individual angles in a certain way. And it's a very nice way. And we'll do some applications there. We'll get double angle formulas, power reducing and half angle formulas out of all of that. We'll solve some more trig equations, a little bit more sophisticated than yesterday. Really a lot more sophisticated than yesterday. And then my favorite, we'll solve some triangles and use the law of sines, law of cosines, and Heron's formula for the area of a triangle. So we'll exercise all of these things. This is what I think trig was really invented for, this last thing. It's solving triangles. This has so many applications in lots of areas. So surveying, doing ballistics work, forensic ballistics, so knowing where a bullet was shot from given the hole in the wall and where it passed through. Also determining, for example, based on a photograph, determining where that photograph was taken, given the relative positions of, say, buildings in the background. So all of this uses trig, and all of this solves triangles using these things. Okay, so we'll do some of that, and we've already done differential calculus, so we can just cross that off the list. That won't be there. Okay. All right, let's get going. So start with the inverse trig function. So let's recall from day one, a function has an inverse if it's 1-to-1. So the inverse function sort of cancels out the action of the function. So function has an inverse if and only if it's 1-to-1. Now, if it's not 1-to-1, we can always restrict the domain to make it 1-to-1. So we restrict the domain so that we take out any collisions that there are. Collisions are what make it not 1-to-1. So what we're going to do is we're going to have to do that to define these inverse trig functions, because sine and cosine and tangent, they're not 1-to-1 at all. In fact, they're periodic. So you draw a horizontal line, it's going to go through infinitely many places on the curve. So it's not 1-to-1. So we agree on some domain restriction first, and then we take the inverse of that restricted function, and that's going to be the inverse function. Okay, so here's how we can restrict the domain. So here's the sine function. So what we're going to do is just by agreement, we restrict the domain to go from minus pi over 2 to pi over 2. And if we do that, then the sine function runs its entire range from -1 up to +1. So we can't pick any bigger domain than that. Otherwise, it's going to start colliding with itself. So this is the biggest domain we can pick, and it's not the only domain we could have picked. We could have picked pi over 2 to 3 pi over 2, and then it would be decreasing. But we want to be close to the origin, and it's increasing. So this is a natural domain to choose. So we just generally agree that this is the standard domain restriction to make the sine function 1-to-1. And so that's for the sine function. Now for the cosine function, again we'll restrict the domain. So the cosine goes through its entire range from 1 to -1. Now we restrict it from 0 to pi. And we could have restricted from minus pi to 0 or a number of other restrictions, but this is more natural. So these are the two official domain restrictions for the sine, one for the sine and one for the cosine. And then we invert these restricted functions. They're one-to-one. So we invert them, and we get we're going to get these inverse functions this is called arc sine, arc cosine, the other names for them. And the tangent function, we can invert that. So the tangent function looks like that. We'll restrict ourselves to just one of these strips. So from minus pi over 2 to plus pi over 2. And notice that the range is everything. This goes through the entire real line as its range. So when you invert this, the arctangent function is defined everywhere. Remember, the domain of the inverse is the range of the function. Here the range is all real line. So the domain of the arctangent function is any angle, is any value. Whereas the domain, what's the domain of sine inverse? It goes from -1 to 1. So it's only defined for values in the range -1 to 1. Similarly for cosine inverse. All right. So for if x goes between minus pi over 2 and pi over 2 for the sine function, sorry, there should be a sine x in there. Sine of x goes from -1 to 1. I don't know why. I didn't notice that before. Let me get that out of the way. I can't get it out of the way. Can't get it out of the way either. No, I've had this. Been through this before, haven't I? It's getting old, isn't it? Okay. All right. So I'm going to make a correction here. Sine of x goes from -1 to 1. Sine of x is equal to y if and only if sine inverse of y is equal to x. So this is just applying the fundamental equation. So here, actually, it's y. Think of this as y now, as going from -1 to 1. For cosine, as x goes from 0 to pi, I guess that should probably be a y instead. So I'm going to change that to y. Y goes from -1 to 1. So cosine of x is equal to y if and only if cosine inverse of y is equal to x. Now, x and y here are just real numbers, but you should interpret them differently, and you shouldn't mix the two interpretations. That's usually not a good idea. X here is an angle. Think of it as an angle. And think of y as just being some value. It might be it's just some real number. But don't interpret it as an angle. So when you take the sine inverse of something, you're taking the sine inverse of some value. And what you get back is an angle. So the inverse trig functions output angles. They take values and they output angles. So let's keep that distinction going. So here, the domain is strictly between minus pi over 2 and pi over 2. And any y is possible in the range. So tan of x is equal to y if and only if tan inverse of y is equal to x. So the particular x we choose here, if you plug in tan inverse of y, the x you're going to get back is always going to be in this interval. Likewise, if you plug in some y that satisfies this, and you hit the cosine inverse button, you're always going to get back an x between 0 and pi. That's what your calculator does because it follows the conventions. And likewise here, if you hit the sine inverse button, you're always going to get an angle between minus pi over 2 and plus pi over 2. Going on. Let's do an example. So what's the sine inverse of root 2 over 2? Also called the arc sine. Arc sine of root 2 over 2. So root 2 over 2 is a value. Does it look like it might be a value corresponding to a special angle? In this case, it actually does. And again, you wouldn't know that by any rule except to look at your special angle table, which you may or may not have memorized by now, and just notice that it's one of those values in there. All right, so root 2 over 2 is the sine of what angle? 45 degrees, but it's not just, that's not the only angle that gives you root 2 over 2, right? So if we draw the line root 2, y is equal to root 2 over 2, we're going to get 45 degrees, unit circle method. We'll also get, what's that? That's 135 degrees. Okay. This is pi over 4. This is going to be 3 pi over 4. Okay. And and we'll get infinitely many angles because we'll have anything coterminal to either of these will also be a solution. But this is only one value because there is only one angle, such angle that's in this official interval from minus pi over 2 to plus pi over 2. On the unit circle, where is that interval? It's basically from there to there. So plus pi over 2, which is plus 90, and minus pi over 2, which is minus 90. That you always take that angle. So it's got to be in that range. Okay, for the sine inverse. Okay. And there will always only be one solution for any possible y value. There's going to be one unique angle in this crescent-shaped range that's going to give you that sine. Okay, so without further ado, pi over 4 is the solution. All right, yeah, question.
I might be trying to oversimplify this, but so for all of the inverses, they're only going to be the angles in quadrants 1 and 4?
For the sine inverse and the tangent inverse, yes. For cosine inverse, you're going to be either in quadrant 1 or quadrant 2 because you're going to be between 0 and pi. So I'll write that in. This is for sine inverse and for tangent inverse. So you've got another one here. This is what you will get for cosine inverse. It's going to be between 0 and pi, so. And on the unit circle, what's the cosine? Which coordinate is the cosine of the angle? It's the x-coordinate. So notice that for any x-coordinate, there's going to be exactly one angle in this interval that gives you that x-coordinate. That's why we choose it. Okay. All right. So what's the cosine of negative half? Well, we draw the line x is equal to negative a half. See where it intersects the unit circle right there and right there. But that's not in the cosine, that's not in the range of the cosine inverse function. This one is, so we take that one, and that's the angle. What angle is that? It's another special angle. It's 2 pi over 3. Or, if you prefer, 120 degrees. Okay. So I've been using the unit circle method. Here, the slides use the graphing method to find these things. What you do is you draw the horizontal line corresponding to the input value across there. See where it intersects the curve in the restricted domain. And that x value gives you the proper angle. So that's going to be 2 pi over 3. Because that's what that is. Okay? Questions? All right. How about one more? Tan inverse of root 3. This is another special angle in tan. So the tangent of some angle is root 3. So how do we do that using, well, you could do it using this picture. You draw y equals root 3 through there, which is about 1.732. And the x-coordinate where it crosses the red line, that would be the answer. Or you could do it here by drawing a line through the origin with slope equal to root 3. Okay. And then that angle is going to be what? 60 degrees, or in radians, pi over 3. Okay. So it's got to be in this range, right? No matter what the slope is, that there's some angle that hits the line that's going to be between pi over 2 and minus pi over 2, exclusive. Okay. So pi over 3 is the answer. Questions? All right. Okay. A couple more examples. If you take an angle, so there's no animation here, so we'll just have to step through it. You take angle, say pi over 4, and you take its sine, and then you take the sine inverse. You would expect those two things to cancel, right? And so you'd just be left with pi over 4. And that's true sometimes. Okay? So sine of pi over 4, if you take the sine inverse of that, you get back pi over 4. But that's not necessarily true. For example, if you take the sine of 3 pi over 4, well, the sine of 3 pi over 4 has the same, that angle has the same y-coordinate as pi over 4. So the sine of 3 pi over 4 is equal to the sine of pi over 4. So when you take the sine inverse of that, you should get back pi over 4. Why do we get the same value here? Where well, because we're plugging in the same value as root 2 over 2 into the sine inverse function. But here, notice we don't get back 3 pi over 4. Why not? Because it's outside the interval, the official interval that we restrict the sine function to. Yeah. So the thing is, you can take any angle here. If it's outside the official interval and you take its sine, what you're going to get is an equivalent angle that's inside the official interval that has the same sine. Okay. So this is getting cluttered, so I'll draw another picture. Okay. So 3 pi over 4 is where? It's up here. It's this thing right here. So that's 3 pi over 4. Okay. That's where it hits the unit interval. And so the y-coordinate is the sine of 3 pi over 4. So this point is actually minus root 2 over 2, root 2 over 2. That's the cosine, that's the sine. Okay. Now, if we apply sine inverse to that, what we're doing is we're finding an angle whose sine is root 2 over 2, but it's not this angle because this is not in the official interval. What you got to do is draw that line, y equals root 2 over 2, and pick the angle that is in the official interval. And notice it's just, that's the official interval. And so it's actually just the supplement of what you got in this case. Okay. Does that make sense?
Is it a complement, or is that new? That would also put it in one of the quadrants we can use, but I don't know how it affects it.
Which, say it one more time.
Like, because you use the, I forget, the complement or supplement, whatever made the 90 degrees from there, to put it back into quadrant 1.
Yeah, it's a supplement.
Could you put it into quadrant 4 and it still work, or would that?
No, because it's got to have the same value for the sine,
Oh, okay.
so which is the y-coordinate. So it's got to be on the same level, so it can't be down here. Let's do that again with cosine. So cosine of minus pi over 4, that's going to be some value. So draw minus pi over 4. That's minus pi over 4. It gives you that as its cosine. But then if you take the cosine inverse of that, you're not going to get minus pi over 4 because the cosine inverse is always going to be between 0 and pi. It's always going to be in this chunk right here. So how do you get an angle up there that has the same cosine as that one?
Take the blanket line.
Take the vertical line. X is equal to, well, whatever that is, it's going to be, in this case, it's going to be root 2 over 2. And see where it intersects here. It intersects the unit circle in the same spot. So, sorry, this line actually goes through there. It's not drawn to scale. I had a calculus teacher who had this amazing skill. He was just using a chalk on a blackboard, but he had a way of drawing perfect circles. I mean, you could use these circles to calculate pi to like 10 digits. Okay, I don't know how he did it. Like he kept his elbow stationary and just went, and it was just beautiful. It was the most amazing thing. Never been able to recreate it. All right. Sorry, I don't know why I got off on that. So here is, so it's this angle that's going to be the answer, which is plus pi over 4. Okay. All right. Questions?
How did you get plus pi over 4? What
because I'm looking for an angle that has the same cosine as this one, but it's in the official cosine domain for the inverse. So the cosine inverse of anything is always going to be between 0 and pi. It's always going to be from here to here. To get the same cosine value, it's going to have the same x-coordinate on the unit circle. So just by reflection, instead of minus pi over 4, it's going to be plus pi over 4. Okay. All right. Tangent of minus pi over 4. You take the tangent of that and the tangent inverse, then you get back minus pi over 4 exactly. Why? Because minus pi over 4 it's already in that official interval. It's in quadrant 1 or quadrant 4. So you get back the actual answer. The tan inverse of, but if you take 3 pi over 4, this is going to have the same tangent because it's the same slope, it's just in the opposite direction. Like that. From your perspective, it's like that. So it's going to have the same tangent, but the tan inverse is still, again, minus pi over 4 because you've got to head in the direction that's in the direction of the, it's got to be quadrant 1 or quadrant 4, but it has the same slope. So 3 pi over 4, I'll draw another picture. So you're drawing, the tangent of this is the slope of this line, whatever it is, it's actually minus 1. This was 3 pi over 4. Okay? So there are exactly 2 angles that give you the line with this slope. Two angles up to being coterminal. This one and this one. But the minus pi over 4 is in the official domain of the tangent function, the official range of the tan inverse. So you're going to get back minus pi over 4. In this case, these will always differ by some multiple of pi. If you take the angle you start with and the angle you get out, they'll always differ by some multiple of pi. Here, well, it may be a little more complicated. Probably the easiest thing is to draw a picture.
On the
Okay. So if it comes to you, that's fine.
Good question.
All right.
Very good question.
So how about the cosine inverse of the cosine of 3 pi over 2? What is that? Tell me what that is. Now I've got the animation on my side without peeking. What is the range of the arc cosine function? It goes from 0 to pi. So 3 pi over 4 is already in that range. So this should give you back 3 pi over 4. And in fact it does. So the point is, y is equal to this cosine. 3 pi over 4 is in that official range, so the answer is 3 pi.
Okay, I came back.
Yeah.
For sine, so for sine and cosine, can you not just add or subtract 1/2 pi?
No, in this particular example, yes, but that's just by accident.
Okay, never mind.
So if you take, for example, the sine inverse of an angle like that, then it's going to be, whatever that angle is, you're going to get this point. You draw that line to get the point in the official spot, and it's going to be that. It's actually, if the angle you start with, if you take it to be at between, say, pi over 2 and 3 pi over 2, then the angle you get by plugging in those two things is actually going to be its supplement, or it's going to be its reflection across the x-axis. Okay. So it's not a matter of subtracting a constant angle. You're actually going to this reference angle and that reference angle are the same. Okay. And similarly for cosine, if you have a let's say a line down here, and you take the cosine of this and then the arc cosine of that, it's going to give you this point up here reflected in the x-axis. Okay, so you can play these reflection tricks and always find out what the answer is going to be. Okay. Here's one useful identity that's actually not on the slides, but it is in the book. It looks a little bit like the Pythagorean identity. For all x between -1 and 1, the sine inverse of x plus the cosine inverse of x is always equal to pi over 2. So it looks kind of like the Pythagorean identity. Kind of. That's how I remember it. Okay, so this fact is always true. It's nice because it relates the sine inverse to the cosine inverse. So if you can find one, you can find the other. And you don't have to take square roots. That's the nice thing. So you don't have to worry about which solution you're going to get. All right, shall we go on then? Here are the graphs of these inverse functions. So here, the green is the graph of y equals sine of x, restricted to the domain, minus pi over 2 to plus pi over 2. That's the green. Now, to get the graph of the arc sine, we flip that graph in the line y equals x. And we reflect that, and then we get the red line. So the red line is y is equal to the sine inverse of x. Its domain is -1 to 1. So that's the only x's that work. And its range is minus pi over 2 to plus pi over 2, inclusive. Now we do the same for cosine. So now the green line is y equals cosine x, restricted to 0 to pi. We flip that across the line y equals x, and we get this red line, which is now decreasing. This is increasing. This is decreasing. Its domain, again, is -1 to 1. and it decreases from pi to 0. So its range is the interval 0, pi. Okay, so that's what the cosine looks like. Now you can almost see this. If you take this line and add it to that line, you're going to get a constant. It's going to be up at pi over 2. Yeah, you're going to get it's going to be exactly pi over 2 always. Questions on the graph? Okay. Here is the tangent function. So again, the green line is the tangent function restricted to that interval 0 to pi exclusive. Flip that and we get this graph. The domain is everything. The entire real line, what's the range? It's the negative pi over 2 to pi over 2. Do we include the endpoints?
No.
No. Right. So it's the open interval minus pi over 2 to pi over 2. Instead of the closed one. All right. Good. All right, let's do an example where now we're going to combine these in two different ways. So this is different from before. Before, we took an angle, applied a trig function, and then applied an inverse trig function to it. Here, we're going to take a value, apply an inverse trig function first, and then apply the trig function, apply a trig function afterwards, possibly a different one. So, let's evaluate tangent of the sine inverse of 2/5. So 2/5 is between -1 and 1, so it has a sine inverse. Well, here's how to do this. Think of it this way. Call this inside thing, it's an angle, right? These inverse trig functions return angles. So let's call this thing theta. What we're trying to find is tangent of theta. What do we know about theta? Well, we know that it's in the official range of the sine inverse function. So it's between minus pi over 2 and plus pi over 2, which tells you what quadrant it's in. Well, it's either in quadrant 1 or quadrant 4, right? So that gives you the quadrant information. But we also know that its sine is equal to 2/5 because it's the sine inverse. So now we know how to solve this from yesterday. We've seen examples of how to solve this from yesterday. So we're in either quadrant 1 or quadrant 4. The sine is positive, so what quadrant does it have to be in? Quadrant 1. Right, sine is negative in quadrant 4. So, and what we want to find is tangent of theta. So we could use some identities. This is one method, or we could draw a triangle. That would be the other method. So let's use identities first. Tangent of theta is sine over cosine. We know what the sine is already, so now we've got to solve for the cosine. So to find cosine, we use a Pythagorean identity and solve for cosine of theta plus or minus the square root of 1 minus sine squared theta. Is it plus or is it minus? We know this. It's going to be plus. Why is it plus? Right, because we're in quadrant 1. Even if we were in quadrant 4, it would still be plus. So this information by itself tells you that the cosine is going to be plus. Okay. I know. I seriously know that I have fixed this. I have fixed this probably more than once. And somehow it unfixes itself. Sorry. You can kind of read that, right? I don't know what happened. I think it's upside down is what the problem is. Yeah, if you look at it's reflected. If you reflect it up in a horizontal mirror. So take a mirror and go like that. It will be fine. Okay. So it's plus. All right. So sine squared is 4/25. So subtract that from 1, and you get square root of 21 over 5. Plug that back into the formula for tangent, and we get 2/5 over root 21 over 5. 5's canceled. We get 2 over 21. Bless you. Or 2 square roots of 21 divided by 21. That's the answer. That's tangent of theta. right. Questions? You could use a right triangle instead. So sine is positive, so we're not in quadrant 4. We're in quadrant 1, and I get 2/5. So draw a triangle with opposite 2 and hypotenuse 5. Okay. Solve for the adjacent, it's root 21, and then just take the right ratio for the tangent. It's going to be opposite over adjacent. And we're in quadrant 1, so everything's positive, everything's good. We're all good. All right. So, okay. Questions on either of those? So you should be able to take some value, take an inverse trig function of the value, and then take a trig function of that, possibly a different one, and give the answer. What if we took some value, took its inverse trig function, and then applied the same trig function to it? So now we have sine on the outside and sine inverse on the inside. What happens?
It's in the interval.
Yeah, well, assuming that the value I start with has to be between -1 and 1. Otherwise, it's undefined. But yeah, once we assume that, then we always get back the same thing. So a trig function and its inverse cancel if the inverse is on the right. The inverse function is on the right, and the trig functions applied afterwards, they always cancel and just give you back the same value. The problem comes when the inverse trig function is applied after the trig function. Then you've got to do this little adjustment of the angle corresponding to getting the right interval. Okay. But if you apply the inverse trig function first and then the same trig function afterward, it just cancels. All right. But we're not going to do that because that would be too easy. Let's try the cosecant of the cosine inverse of -2/3. Same method. Cosine of -2/3, cosine inverse is some angle theta, and we know based on this we know things about theta. It's a cosine inverse, so it's got to be in the official range of the arc cosine function. So it's got to be between 0 and pi. And its cosine is -2/3. So, applying the methods of yesterday, we can get it. So this is going to be either quadrant 1 or quadrant 4. Cosine is negative, so it can't be quadrant 1. It's got to be quadrant 1 or quadrant 2. I was reading that wrong. So it can't be quadrant 1 because cosine is negative, so it's got to be quadrant 2. Great, so we draw a triangle, say that way. And we got 2/3. Solve for this. This is root 5. And so the cosecant is 3 over root 5. Or 3 square root of 5. The sine of tan inverse of -3. Again, call that inside thing, call that angle theta. This is, we're finding sine of theta. What do we know about theta? It's in what two possible quadrants?
It's in quadrant 2.
No. It's 1 or 4. Yeah, so the sine inverse and tan inverse have the same two quadrants. It's 1 and 4. It's only the cosine that's 1 and 2. Okay, so this has got to be quadrant 1 or quadrant 4. And what else do we know about theta? We know that its tangent is what? -3. Okay, all right. Maybe that's what you said. I didn't quite hear you.
So we're looking at.
All right. Oh, jeez. Sorry. And let me just bear with me just 1 second. I apologize for this. Flip. Just reset. Okay, so tangent of theta is -3, and we want to find sine of theta. So we're in quadrant 1 or quadrant 4. The side is minus 3, so we've got to be in quadrant, what, 4? Okay. So we could draw a triangle this way, put a 3 and a 1 there. What's the hypotenuse then?
No. Square root of 10.
Square root of 10, yeah. If you were thinking if it's 1 and the square root of 3, then it would be. Okay, but no, the square root of 10. All right, so now we can read off the sign. It's going to be minus 3 because we're the opposite is minus. It's going to be the minus divided by 3. Okay, or minus 3. All right, do we want to do any more of these? No, we don't. Ah, yeah, nice picture. So this one is the range of the sine inverse and tan inverse, and in this range, the cosine is always at least 0. The range of cosine inverse. I'm going to put the inverse in there. I didn't. The range of cosine inverse is 0 to pi, and in that range, notice the sign is always positive or 0. Okay, so this last part of that will actually be useful to remember when we get to triangles. All right, well, I'm going to skip this, but skip part A. Let's do part B. So we're going to use a right triangle to rewrite this as some algebraic expression in X, so not involving trig function. So cotangent of the sine inverse of 3x. Well, we could do what we did on the previous slide, except now we're using expressions instead of concrete numbers. The same idea. Call that thing theta. We're trying to find the cotangent of theta, and we write down what we know about theta. Sine of theta is 3x. Well, we don't know what x is, so we can't tell if this is positive or negative, but we do know what? About theta, at least. It's going to be in quadrant 1 or quadrant 4. Less. So we could either draw this in quadrant 1 or quadrant 4, but in any event, the adjacent here is always going to be positive, because that's the x coordinate.
How do you know that's always in 1 or 4?
Because it is the arc sine of something.
So
The arc sine, the range of the arc sine is in this piece. So from the previous handwritten slide, it's quadrant 1 or quadrant 4.
So whenever we apply the picture rule, it's dependent on the arcs.
Yeah, depending on what arc trig function we're taking. Yeah. So sine and tangent, well, we're only going to use these 3. We're only going to use sine, cosine, and tangent. We're not going to use the other 3. That was why I skipped part A, because it's arc cotangent. Arc sine and arc tangent are both quadrants 1 and 4. Arc cosine is quadrant 1 and 2. So this is quadrant 1 or quadrant 4, but in either quadrant, the x-coordinate is positive. So when we compute the adjacent, we take the positive square root when we do the Pythagorean. And so now we can just read off the cotangent, which is adjacent over opposite. So it's square root of 1 minus 9 squared divided by 3x. So this is an expression that's equal to this that does not involve any trig functions. Okay, so that's you can do that with any combination, applying an arc trig function first and then another trig function afterwards. You can always get an algebraic expression for it. What x's is this defined for?
For negative 1 to 1.
Nope, that's too big. Nope.
I'm going to say...
You get 2 chances at this. And then I got to interrupt you. All right. The domain of arc sine is what? the domain.
Negative 1/3 to 1/3.
Okay, you're answering my previous question,
Yes,
not the
sorry.
question I just asked. All right, so the domain of sine inverse is negative 1 to 1. So 3x has to be from negative 1 to 1. So x has to be from negative 1/3 to positive 1/3. Another way to see that is if you take 9x squared and subtract it from 1, if this will be negative if x is outside that interval. And it'll be 0 or positive if it's inside. So this won't even be real if x is outside either. All right. Good time to take a break. Let's take a break. Yes.
What about when x is equal to 0?
No problem. If x is 0.
This is an issue with our algebraic.
Oh, I see. Yeah. Okay, you're right. X is equal to 0. That's you can't divide it by 0, right? And that's because the cotangent of 0 is undefined. So yeah, we gotta restrict those two restrictions. I'll mention that.
So you're just looking at 3x. So it just makes sense to me to just convert that back to times what times x gives you just
Yeah, right. Divide everything by 3.
So that would be true for EM or EM.
Yeah. Yeah. Oh, I got it right there.
I didn't know if you guys did it together or no, we put all the
Oh, yeah. So if I hear you put it here, yeah.
also
Depending on how hard it's going to here.
Since our time is one negative, so for x, I get 1/3 negative 1/3.
She said he's taking to the doctor today at like 2:20.
Party night at the babysitter. It's time to go out.
I know what those are like. I couldn't bring my son won't have it. Now the babysitter, not with him being sick.
We braved the outdoors, the three of us together. It's very controlled.
Crazy outdoors.
You know,
How did
just been fed, just been changed. You know, we're going to be out for this long. We've got food. You know, get fussy type of.
He had a boy, didn't you, sir? How old is he?
Right. 9 weeks past that.
Okay. It's about when my wife would not go out the house until at least he was after 6 weeks, unless it was directed to the doctor for like a well checkup.
That's kind of where we're at. And she's like,
Yeah.
I want to go tonight. I'm like,
Yeah, she would.
Our original goal was 3 months,
Yeah.
but we backed it up back 2 months. But still, it's like very limited that we've actually gone out.
Yeah, it was a minimum of like, I think it's 6 weeks. It was like a minimum of 6 weeks. Like she didn't even go to church and whatnot. I would just take the other ones and stuff like that. She no. Going on, and I was like, I fully support you and understand. Some people in the church, they got their like newborn. It's like they pop the kid out the next day, and I'm like, oh.
no, what's crazy is when they like let everybody touch the kid by washing your hands.
What are you
doing? Adults are
That's a big negative.
She got this.
something more. Well, I was on 3 days, so less than 10 days, and have more to go. 2-hour drive.
I've never gotten
went out to the aquarium. By Christmas time, we went on a 4-day trip to Fairbanks.
How old was he?
He was born on the 4th.
Oh, wow.
By the weekend before Christmas, we went on 4 days out to Fairbanks.
Now, don't get me wrong.
20 days later.
Yeah, don't get me wrong. The first 2, I think we were beat out there. We were beat Florida, and I was in the military. We were beat from Florida to South Florida. By the time they were getting whatnot.
The first one seemed to yeah, and he turns it off. Find some my computer away.
Like if this was CCNA, everybody would just be like,
yeah.
this is the only way I'm taking it away. Just one person.
I'll probably stay away.
How about over 2 or close to 2 are you?
He just turned on yesterday.
Oh.
And then between 4 or that's
That's the problem. We went to a swimming place over like a couple trees after this. And we thought we'd also look at some toys. He's all about shaking with everything.
He's one of those fancy ones, sir.
And there's just no sword. Jigsaw, go home! Jigsaw, go home! What? What? But maybe they were having what? He's like, no, it's going down.
We're like,
yeah, I can be. For whatever reason, my youngest son's Gavin, the writer. Gavin calls Ryder yellow. I don't know why that's easier to say than Ryder. So like for 3 months now, I called him yellow.
Fuck that. Fuck that. Your name's Yellow.
This morning, I get home from tea and all I hear is, no, yellow, no, stop it. Stop it, no. It's a screaming and I pop my lung.
I know if you got one of those or those crazy. Have you seen those that like the car seat fits into the actual stroller and you can pull it out?
That's what we're doing. It's not like it's made to fit in, but like you kind of just set in that car. Yeah.
And when I unfolded it, I hit my shin. I was like, have you had to go to the shaking baby class? They fucking make you do it.
Yeah.
If you're a big kid now, it's a requirement.
Yeah, on a military, like, you have your child's on post.
We all have those.
So we sound like,
I think it's not it's all I remember about when I first met him. Never shake a baby, and me and her got fleeced. I don't know why people say don't shake your baby. Look, he loves it.
I had to like move the car the whole time. It was really bad. I was out riding to get some blood figure out at the doctor. I was holding Gavin. Like just gut reaction. And then like right when someone's walking, I'm like, oh jeez, I'm gonna go.
This is like
It wasn't like hard, but like what else are you gonna do when someone bites you?
yeah. A few weeks ago, luckily we were at the house. My kid, and he just rushed back. You know, it was just a response. Not anymore. No, I was like, I was like, you can learn. I guarantee you. One person that asked me about this is, real quick, everyone. Tonight's social is going to have. I don't know if it's going to have all the 24s on post, but it'll have a good many of them. It's voluntary. You don't have to come tonight. would strongly encourage, because one, this is your branch manager, you're going to see him, you're going to want him eyeball to eyeball, you need to punch him in the face, an informal event. But the other side of that too is, if you're having a family crisis right now, then, that's okay. We got that. But do come tonight. There might be people you can ask about what they do, how to engineer network, and other stuff. So,
do we know if we're doing the indoor or outdoor seating at Reinhardt's?
I do not know. So,
We're later. Yeah, that's what I'm trying to get.
But Joe and Ryan can just walk in the room. Tonight's event is informal and not mandatory. So, if you can't make it or you have other things going on,
just don't leave out whenever you agree it.
You can decide to Hawaii.
Yeah, highly encouraged, just the same.
Whatever, I'm going to Kansas anyways.
Thank you, sir.
No problem. Thank you.
It's on there. It's like number 3.
So let me just point out, just from before, so the domain of this thing is actually, we said it was minus a third to a third. Well, we got to also exclude 0. Because, well, you can't divide by 0 for one thing. The other way to see it is that, remember, if you have the composition of two functions, to be in the domain, you have to be in the domain of the first function, and then that output has to be in the domain of the second function. And cotangent is not defined. The cotangent of 0 is not defined. Infinity. It's one of those asymptotes. All right, so got to exclude it. That's all I need to say. Okay. So I'm going to skip this. I'm going to skip that even though we